Today on Science Max, we're looking at
Chemicals!
Chemicals make up everything around us, and we're finding out which ones you can mix together to make spectacular science.
Whoa! Woo! Cutest science ever.
Today on Science Max, experiments at large.
Greetings, Science Maximites! My name is Phil McCordick, and the name of the show is Science Max Experiments at Large. Today, we're taking a closer look at chemistry. Ooh. Chemistry is the science of atoms and molecules, the things that make up all matter, and how they interact with each other. Take, for example, this glow stick. Actually, don't take it, because I kind of need it. The glow stick doesn't glow until you... The glow stick doesn't glow until you break the barrier and mix the two chemicals, and they start to glow. Huh? Pretty cool, huh? Chemistry. Now, the chemical reaction we're looking at today is the old vinegar and baking soda volcano. But this reaction doesn't have anything to do with volcanoes. It's chemistry. Now, this experiment is totally safe, but I do recommend you get an adult's permission before you do it because it's very messy. Yeah. First, you're gonna want baking soda and vinegar. These are your two main ingredients, but you'll also want dish soap and red food coloring if you want it to look a little bit more like lava. Now, I like to mix the baking soda, red food coloring, and dish soap together with a little warm water, so all you have to do is add the vinegar. And when you do, this is what happens. And there you go, chemical reaction. Now, I know what you're thinking. You're thinking, Phil, how much vinegar or baking soda do I use? Well, I'm not gonna tell you. This is where you can be Science Maximites. Try different amounts. More vinegar, more baking soda, more dish soap. Who knows? Write down the amounts each time you use it and find out what amounts work best. That's called science. And that's what we're gonna be looking at today. Chemistry in all its forms. And of course, because it is Science Max, experiments at large, we're going to max out the vinegar and baking soda volcano. So I'm off to the Center for Skills Development and Training. Come on. Hey, Talina.
Hi, Phil.
How you doing?
Good, how are you?
Good. This is Talina. She's going for her PhD in chemistry from McMaster, right?
Yep.
Awesome, which means you can help me max out the baking soda and vinegar. We need vinegar. You grab that vinegar. And vinegar volcano. So what happens when we mix these two chemicals?
Well, vinegar is an acid and baking soda is a base, and when you mix them, they neutralize each other to produce carbon dioxide and water as a byproduct.
So acids and bases are kind of like opposites.
Yep.
So I guess that makes sense. When you put them together, crazy stuff happens.
Yeah.
Awesome, chemistry. Okay, so I want to use this much vinegar and this much baking soda.
What's with the fish tank?
The fish tank is where I want to mix it all together. What do you think?
Awesome.
Maxed out. Okay, let's move the fish tank somewhere where we won't make a huge mess. It's a little heavy with all that. We gotta, no, we're gonna have to take a couple trips. That's kind of heavy. Okay, so we'll take this and that, and then this, and that. No, hold on. I can do it. One more. Okay, good. Okay, good. Yeah. I took too much. Uh-oh. That's good, Ramona. Put it in the background. Put the sign in the background. Yeah, in the BG. I love the BG. Chemicals. What are chemicals? Are they things you have in a lab in a jar that say chemical on them? Well, yes. But if that's all you think chemicals are, then you need to know your chemicals. Turns out the stuff in the jar is a chemical, but the jar itself also made of chemicals. The table I'm putting it on. Made of chemicals. My lunch? Chemicals. Roller skate? Chemicals. My jacket? Chemicals. This guitar? Chemicals. My shoe? Chemicals. This watch? Chemicals. This fish? Chemicals. 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 Me? Chemicals. You? Chemicals. Ramona? Chemicals. No, I said your chemicals. Never mind. This is it. The periodic table of the elements. All matter in the universe is made up of these pure elements. They go together in different ways to make up everything. All matter. Think of it like building blocks. These little atoms are some of the elements on this periodic table. You got 1 oxygen, 2 hydrogen, bam, you got a water molecule. 1 carbon, 2 oxygen, hey, it's carbon dioxide. 2 carbon, 2 oxygen, 4 hydrogen, skadoosh, vinegar. 1 sodium, 1 chlorine, hey, that's salt. All matter in the universe is just the stuff on here combining into these. And now, you know your chemicals. Sugar.
Let's take a closer look at what's going on when we mix vinegar and baking soda. All chemicals are made of atoms. There's only 4 types in our reaction: carbon, oxygen, hydrogen, and sodium. When they go together like this is a molecule of vinegar, or acetic acid. And this is a molecule of baking soda, or sodium bicarbonate. When chemicals react, they switch atoms. That one goes there, this one goes over here, and then this one turns into this, and then what you end up with are new molecules. This one is called sodium acetate, and this one is carbon dioxide gas, the gas you breathe out. And do you recognize this one? Right, water, H2O. Why all this happens gets complicated, but the study of chemistry is all about how molecules are built and react with other molecules.
All right, Talina, you ready?
Yep.
You're gonna pour all your baking soda in the fish tank, and I'm gonna pour the vinegar into this bucket, because you don't wanna pour them together right away. Okay, you ready?
Yep.
Okay, go for it. When you're doing your PhD in chemistry, do you get to do stuff like this?
Yeah.
Really?
Got to do a lot of fun reactions in the lab.
Oh, I'm jealous. Have you ever done this much vinegar and baking soda in one time?
I can't say I ever have.
There you go. That's what I like to hear. I already put the soap in the bucket so it would mix with the vinegar when I poured it in. Are you done your baking soda already?
I am.
I'll pour faster. Oh, faster.
It smells vinegary.
It smells vinegar. It makes me want French fries. Okay, Talina, you take this very full bucket of vinegar and dish soap.
Thank you.
I will take this one. Uh-oh, we still have our 3rd bucket. Okay, I'll do these both at the same time. Okay, ready? On the count of 3. 1, 2, 3. Whoa! 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 Wow.
Okay.
That's awesome. So the one thing it didn't do, it didn't shoot up in the air though.
Yeah, it's because the top is quite open, so you would need to constrict it to get it to shoot up.
Oh yeah, because we're using just sort of a square, a rectangular prism container. We should get something that's maybe something more like our vinegar bottle, right? Because there's lots of space down here, but then it forces it into a tighter opening at the top there, like a volcano.
Yep.
And what else can we do to make it even more powerful, to max it out?
Vinegar is only 5% acid, the rest is water, so you could try using 100%.
So what kind of acid is vinegar?
It's acetic acid.
So vinegar is actually only 5% acetic acid and 95% water. So you can get 100% acetic acid?
Yeah.
Can you get 100% acetic acid?
Yes.
Awesome. Why don't we get a container that's sort of shaped like a funnel, like a volcano,
Yeah.
and 100% acetic acid, and we'll do it again.
Sounds good.
All right, let's do it.
Our vinegar and baking soda reaction went pretty well. But now we're gonna try it with a much stronger type of the same kind of acid you find in vinegar.
Carefully putting this down. And watch out for the baking soda. You never know when it'll get out. And, well, I guess that's just baking soda, huh?
Yeah, that's pretty safe.
Yeah, okay, good. So this is baking soda vinegar volcano version 2. We have this differently shaped glass. What do you call this again?
That's an Erlenmeyer flask.
Why is it called that?
It's actually named after a scientist.
Did he look like that? Was he sort of shaped like this?
No.
No? Was he just a good chemist?
Good scientist, and I think he designed the glass.
Oh, see, there you go. So if you want to have a glass named after you, be a good chemist and design a glass. I want to make a fill beaker. So this is 100% acetic acid.
Yep.
And what's the difference between this and vinegar?
Vinegar has 5% of this and 95% water. But this is 100%, so it's much stronger.
Much stronger. Can you put this on your French fries?
No, I wouldn't be putting it on your French fries.
No? As chemicals go, how dangerous is this?
It's not too dangerous, but you definitely don't want to be breathing it in, and you don't want to be eating it.
Or getting it on your skin. That's why I'm wearing these fancy gloves. So what I'm gonna do is I'm gonna pour the acetic acid in this. What's this called?
That is a graduated cylinder.
Because it finished school. So it graduated. Now you're gonna mix water and food coloring and soap all together.
Yep.
And pour it into there?
It'll help dissolve some of the baking soda, so hopefully it'll react better with the acid.
Sounds good. Face protection.
Oh.
All right, that's good. And now, when we do it, I want to add the funnel at the end to like accentuate the concentration of, but I don't know if it's gonna go so fast that I won't be able to get it in there, but we'll try it.
Try it.
Vinegar baking soda volcano version 2. Woo!
Good thing you got the mask.
It smells a lot like vinegar. It's really strong.
Oh.
That was pretty good. But what can we do to make it even bigger?
Well, you could try using a different chemical reaction.
Ooh, okay. Like what?
The decomposition of hydrogen peroxide produces oxygen gas, and so that one's pretty vigorous if you use a catalyst.
So we want something that makes a lot of gas so that it makes a lot of bubbles when you put the soap in it.
Yep.
Great, let's do it. And the sooner we leave that smell, the better, I think, for my taste. Today we're combining two different chemicals to create a reaction. Sometimes chemicals can combine in a way that makes them very different from how they started out. For example, this is sodium, or Na on the periodic table. Now, the sodium tablets are in mineral oil because sodium reacts very strongly with water, even the water in the air, or especially the water in my skin. Watch what happens when I drop a sodium tablet into this beaker of water. Very cool and very dangerous.
And this is chlorine, or Cl on the periodic table. Chlorine gas is very poisonous. So,
So, what happens if we combine these two deadly substances? Do we create some sort of super poison? Something more deadly than anything else known to science that causes fear and chaos in chemistry labs all over the land? No, we create salt. Good old normal table salt. These two substances combine to make NaCl, salt. Something completely and totally safe. Chemistry. Oh.
We've gone from vinegar and baking soda to 100% acetic acid in baking soda, and now we're doing the
Vinegar and baking soda volcano version 3. No longer vinegar and baking soda.
Nope.
What are we using this time?
So here we have some hydrogen peroxide.
Oh, that's the stuff you use at home to put on a cut, right?
Yeah, but the stuff at home's only 3%. This one's 30.
So much stronger,
Much-
10 times stronger.
Yes.
And is this more dangerous?
It's definitely corrosive, so wear your gloves.
Corrosive means it could eat your skin,
It can burn your skin a little
which
bit.
is why we're wearing gloves and blast shields. What's gonna mix with this?
So here we have some potassium iodide, which is a salt, and it's mixed in with some water.
The most important part of this reaction is the fact that it creates gas,
Oxygen
which
gas?
makes bubbles when you put in dish soap, right?
Yep.
So one big squirt of dish soap like that. Mix it up. Now we go over to the blast zone.
That's plenty.
All right. Now that's a reaction. Looks like there's steam coming off here. Why is that happening?
Well, it is an exothermic reaction, so heat is being generated as the reaction proceeds.
Oh, cool. Can we lift our visors now?
Yep.
Awesome. And what's being released? What's the gas that's coming off here?
So it's oxygen gas that's being produced.
Oxygen. What we want to do is make this even bigger, but first, can we do it again?
Sure.
Because I have an idea. Hold on. I think we should repurpose our old volcano. What do you think?
Sounds like a good idea.
Okay, so if we put it over here. All right, volcano version 3.5. Hydrogen peroxide, potassium iodide. Right, here we go. Whoa!
Looks like lava.
Whoa! Look at that. Now that is a big volcano eruption.
Just covered the town.
That is completely, yes. That town is gonna be very clean because it's all soap bubbles. It's the cleanest volcano this side of Science Maxville. So I still think we can do this bigger, though, right?
I agree.
Oh, I know. What if we use some sort of a tube, like maybe one of these, right? And then we attach it to like an air compressor.
I think you'd get some height.
Yeah, and we go outside.
The atom in 60 seconds.
The atom is the smallest unit in a chemical element. Atoms are made of 3 parts. Part number 1 are these guys, protons. They have a positive charge. The number of protons determines the element. 1 is hydrogen, 2 is helium, 3 is lithium, and so on. The protons sit in the middle here, which is called the nucleus. They sit in here with part number 2, these guys. They're neutrons and they have a neutral charge. Now I've got 8 protons and 8 neutrons in this nucleus, making this an atom of oxygen. Orbiting around the nucleus are these tiny guys. They're electrons and they have a negative charge. I will demonstrate using kittens.
Kittens are perfect because just like electrons, kittens are really small. And just like electrons, kittens move around randomly. You never know where they're going to be, but an oxygen atom should have 8 kittens, or electrons, somewhere inside. These kittens are constantly escaping, but guess what? That happens with electrons too.
There you go, the atom, a nucleus of protons and neutrons surrounded by randomly moving electrons. Cutest science ever. How do you guys feel? Did you learn something? Huh? Pause up. Who learned something?
Talina and I have made a bunch of chemical reactions, but in our quest to max things out, we've got a new plan.
Whoa.
Hydrogen peroxide and potassium iodide create gas. One way to max out the reaction is to contain the gas in something like a tube. We're gonna put the hydrogen peroxide in the tube first. Then we're gonna put in the potassium iodide in the top through a one-way valve. Then we're gonna pressurize the container. When it finally reacts, it will shoot up through the valve and we'll see how high we can get our stream of bubbles to go. But be warned, capping anything and not letting it escape is never a good idea. So we've got a release valve to make sure things work out. This is one of those experiments that's definitely on the list of don't try this at home.
Vinegar baking soda volcano version 4, hydrogen peroxide, potassium iodide. And what we're gonna do this time is we're gonna put it in this tube. Hydrogen peroxide goes in here. And we've got, Talina, do you have the potassium iodide in syringes?
Yep, 2 syringes full.
2 syringes full. About there is good. And then soap. Good amount of soap in there. And so what we're gonna do is we're gonna close this off and tighten it up. And then we're gonna pressurize the whole system. And then we're gonna add the potassium iodide. And it's going to be spectacular, we hope. Okay, that's on tight. This is all good. Putting this down here. And potassium iodide goes in here.
Ready?
Puts down. Ready? 1, 2, 3, go. And we back away slowly. Whoa! Whoa! Yeah, that's what I'm talking about. Okay, let's check it out. Woo! All right, there you go. Vinegar and baking soda volcano maxed out. Thank you, Talita. That was great. If you guys want any instructions for the stuff that we've done today, they're all on the website. And thank you very much for watching Science Max Experiments at Large. We kind of need to clean up a lot, don't we?
Yeah.
We have out here, we have the other room. So tell you what, you get a mop, I will get the hose and a wheelbarrow for this.
This episode is all about chemical reactions.
Nom nom nom, nom nom nom, nom nom nom, delicious.
Reactions to make things fly, to make things glow, to make things pop, and to make things fly.
That worked.
Wait, did I mention the flying? I'm sure I did, but I'm mentioning it again because it's awesome. All on this episode of Science Max Experiments at Large.
Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemistry! Chemical-powered rockets! Away! Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when two molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between two kinds of molecules called acids and bases. Like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a film canister. And ask your parents what that actually means because they're not used for holding film anymore. You can get these at craft stores, though, to hold paint or little things. But really, all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then, of course, what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. Come on, let's max it out. So first, I need an expert to help me. Lisa from Logix Academy, of course. Logix Academy people have helped me launch all the rockets on Science Max. This is gonna be great. I'm gonna get my helmet first. Okay, let's launch some rockets! Let's go!
Whoa, wow, it's really dark in this room. I can't see anything.
Phil?
Lisa?
Phil?
Lisa?
Phil?
Where did this come from? I guess the portal's malfunctioning. Hey, Lisa!
Hi!
From Logix Academy, great to have you here.
Great to be here.
Let's put this over there. We are here to max out the chemistry rocket!
Ooh, what is that?
It's just a small plastic container. But when we put an antacid tablet in there and some water,
We get a chemical reaction.
we get a chemical reaction. And so that's what creates the pressure. And then that pops the lid off and we get a little rocket.
Kaboom!
But now we're going to max it out. Get a bigger container and more...
Wait.
What?
How about if we launch a whole bunch of them?
Ooh, so we just get a lot of the small one, and we launch them all at the same time.
Exactly.
Okay, great. So we just need a whole bunch of these and a whole bunch of...
And a whole bunch of science antacid.
Yeah, well, that's okay. I get them both in bulk. Come on, let's go put it together. I'm an acid, and I'm a base, and we are enemies. Whoa, well, we're not really enemies. Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons.
You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react.
Whoa. That is until water gets involved. Once you have water, acids and bases react. Whoa. Here, take some protons. All your bases belong to us. Here you go. Take some protons. I don't need more. I want more. I want more protons. Here.
Water is a solvent, allowing the chemical reactions to take place.
Depending on the strength of the acids and bases, that reaction can be mild.
Would you like a proton?
Oh, no, really, I could.
Please take it.
Oh, well, thank you, that's very generous.
Have another.
No, perhaps, maybe I will.
Here's
Yes,
one.
Okay, maybe just one. But if the acids and bases are strong, the chemical reaction can be really extreme.
This is what's going on in the antacid tablet, and why, without water,
Nothing happens. Oh, water! Water! Come on!
what'd you do?
What?
And that's the last one.
Lisa and I are maxing out our chemical-powered rocket not by making it bigger, but by making more of them. How many more?
400 caps all glued down. 400 antacid tablets, or part of,
Yep.
all glued down, and they're glued on this fancy-pantsy spinning surface. So we rotate this part upside down.
We fill each container with a little water and snap it on underneath. This way, the antacid tablet and the water don't mix until we flip it back over. It also allows us time to snap them all on.
Okay, ready?
Ready.
All right, 400 containers. Here we go.
Let's do it.
Once we flipped the board back over, the reaction started taking place, building up carbon dioxide gas and increasing the pressure until...
What do you think?
Oh, yeah. Oh, yeah. It's good luck if you catch one.
Wow, that one went really high. Oh!
Awesome! That totally was great. Wow. Okay, so high fives on that.
Yep.
That worked spectacularly.
That was awesome.
So we've done this.
Let's go bigger.
Let's go bigger.
Bigger.
Oh, okay. So let's go and we'll clean this up afterwards.
Yeah,
okay.
let's do it.
Okay, let it go. Whoa. Whoa. This is a balloon, and this is an orange. When you put them together, a chemical reaction happens. How'd you go in there for a minute, didn't I? No? No? All right. Well, you can actually do a chemical reaction between a balloon and an orange. You see, balloons are made of latex, which is a kind of polymer that's very, very stretchy. And orange peels contain a chemical called limonene. Limonene breaks down latex. So, we have 3 questions. The first is, why does this happen? Well, like I said, it's all chemistry. You see, balloons are made of polymers, chains of molecules held together by chemical bonds. A limonene molecule attacks those bonds. Nom nom nom, nom nom nom, nom nom nom, delicious. And breaks it, that separates the polymers, and that pops the balloon. But remember, it only works with natural latex. So make sure you're using natural latex balloons. Second question, why do they call it limonene when it's in orange peels? I mean, yes, it's in lime peels and lemon peels, but the chemical itself smells like oranges. They should call it orangenine or citrus fruitinide or... Anyway, third question, should we max it out? Of course we should, come on. 200 balloons versus 2 bottles of limonene. Ready? Go! Science! Our first attempt to max out our chemical rocket was 400 plastic containers. Oh, yeah. That worked well, but now it's time to make the container larger. Whoa! Giant maxed out chemistry rocket canister. I have a big plastic container with a groovy lid that sits there on airtight, which is great.
And I have a giant jar of antacid.
How many? It was like 60 antacid tablets or something?
At least.
This works exactly the same as our smaller containers. We dump the antacid in, seal the lid airtight, then flip it over. And now would be a good time to mention not to try this at home. Okay, it's not gonna take long. All right, so that was the canister version. Now we need the pop bottle version, the
Yes.
rocket version.
Yes.
Okay, let's go make that.
Let's do it.
Okay. This is a light stick. It creates light using a chemical reaction. There's a liquid chemical inside and also a glass container that holds another chemical. When you bend the light stick, you break open the container and the two chemicals mix, creating light. There you go, light sticks, chemical reaction. And yes, of course we're gonna max it out. This is a whole bunch of the two chemicals in a light stick. Let's max it out. So how does a chemical reaction produce light? Well, a lot of chemical reactions produce energy. You might think of a chemical reaction producing heat. Well, heat is a kind of energy. This chemical reaction also produces energy, just energy in the form of light. It's just a different kind of energy. Whoa, maxed out light stick! And now for a Science Max quiz. Chemical change or not? What's a chemical change? Well, let's demonstrate. Look at this. It's a happy little molecule of iron. And here's another molecule of oxygen. If they were to have a chemical change, they would react and form different molecules. Look, it's a molecule of rust. Rust is a different chemical than either iron or oxygen. It's a chemical change. Now, if these molecules mixed and did not change, then it's not a chemical change, it's a physical change. Sometimes it's hard to tell if it's a chemical change just by looking, but asking what kind of change it is leads to good science. So let's look at some examples. Vinegar and baking soda. Is it a chemical change? Yes. Vinegar and baking soda react to form different chemicals. Sodium acetate, that's the white stuff that's left over, and carbon dioxide, which makes the bubbles. How about a nucleation fountain with Diet Cola and mints? Haha! A lot of people think that's a chemical change, but it's not. The mints cause carbonation, the bubbles, to escape faster. But in the end, you still have cola and mints, no new chemicals. And without the carbonation, nothing happens. So, it's a physical change. Take a guess at this one. Glow stick chemicals. Well, producing light or heat is usually a sign of a chemical change. How about mixing sugar and water to make a sugar pop? That's a physical change. You start with sugar and water, you mix them, and when you have a sugar pop, what chemicals are you left with? Well, sugar and water. So, no chemical change. It can be hard to tell sometimes,
But whenever two things mix, think to yourself if it's a chemical change or a physical change. And now you know it's either one or the other. And that's the first step to good science. Thanks for playing our Science Max quiz. Our maxed out rocket worked great. Now to make it look more like a rocket.
So we have a mesh bag here to put the antacid in.
Right.
And we have some paper clips attached to it.
And what are the paper clips for?
Well, Phil, we have a magnet.
Ah.
And so the magnet sticks to the paper clip.
And so that's what we have here. You see, the bag is full of the antacid tablets, which we put through the mouth of the bottle, and the magnet is holding the paper clips on the other side of the plastic, so we can sort of move it along. So we can start with the bag over here where the water's down there, but now we attach the launcher, like so.
All this effort is to keep the reaction from happening until the bottle's on the launcher and we're ready to go.
And then, as we pull the bottle over, we bring the bag up this side, and there, the water and the antacid have never touched.
No reaction.
All you need to do now is we pull this magnet away, and the bag will fall into the water. And then we will have the launcher down here, and we pull the release, and the rocket will go.
We add some weight to the launcher to help keep it in place.
Okay, right, wait, glasses.
Safety first.
Okay, ready?
And then we pull the string with the magnet. That drops the bag of antacid tablets in the water and starts the chemical reaction. Because we have a latch holding the bottle down, we can wait until the chemical reaction happens fully. And there's a lot of gas pressure in the rocket before...
3, 2, 1, launch! Woo! That worked.
Yeah, I had hit the ceiling. I think we need to do this outside.
Yeah, I think we definitely have to do it outside.
All right, totally great. Weird. Anyway, I was saying we should put 3 or 4 of them. 3, 2, 1, go! There it is. Yeah!
We tried it outside and it worked great. The only thing left was to max it out even more.
So, larger chamber?
Yep, more antacid.
More antacid, more air, more water.
Absolutely.
Bigger rocket. Okay, so you know what? I know how to splice 2 bottles together, and we can increase the size of the chamber. This is sodium acetate. How do you get sodium acetate?
Well, when you do a vinegar and baking soda reaction, what you have left, once the reaction is finished, is sodium acetate. It's a crystal, and you can do something fun with it that may seem familiar. You make a supersaturated solution of sodium acetate by heating water and dissolving as much as you can, and then when it cools, you can get the crystals to reform.
Now, if you did this with sugar, you could make a sugar pop, which we've done before. If you do it with salt, you could make a salt pop, which is less appealing. And if you do it with sodium acetate, you can do this.
Just like with the sugar pop, all it needs is a seed crystal to get the crystals to reform. But unlike sugar, which takes a few days, sodium acetate recrystallizes right before your eyes. Because we heated the water, it allowed more crystals to dissolve in it.
Ooh.
But then it cooled down afterward. There's more crystals sitting around in this water than there should be at this temperature. They want to turn back into crystals, and all they need is something to start them going.
I've colored this one green because, I don't know, science. Maybe it'll look cool.
A tiny crystal on the end of the stick is all we need to start the reaction happening.
Whoa! Wow. And there you go, sodium acetate. That one wasn't done yet.
We've gone from small containers,
Oh, yeah.
to a large container, to a rocket.
Yeah!
So what's next?
Super maxed out rocket!
12 2-liter bottles all spliced together to give us a very large chamber to build up pressure with.
So the chamber is all the same. So it's all one big hollow tube, and now we're gonna fire it off. Let's go!
Let's do it!
Awesome rocket! Yay!
and I follow the same procedure as before. We use a bag of antacid tablets held up inside the rocket with a magnet. And once it's sealed on the launcher, we pull it off, let the antacid mix with the water, let the chemical reaction happen for a while to produce enough gas pressure, and then we fire it.
Okay, here we go. 3, 2, 1, go!
Oh my God!
That is the highest I think we've ever shot a rocket on Science Max.
That's amazing.
Well done. Chemical reaction rocket. Thank you very much for joining us on Science Max Experiments at Large. We should build another rocket because
I
that
think
one is probably broken.
That's done.
Okay, let's go.
Let's do it.
All right, so this time I think what we should need to do is... Oh no, it's nothing but garbage cans in there. We gotta turn the portal off. Come on, we gotta get... Greetings, Science Maximites. Today we're using fizzy drinks in our experiments. And a fizzy drink is just water with bubbles of carbon dioxide gas dissolved in it. So I thought since we exhale carbon dioxide, I could make a fizzy drink by just blowing bubbles in this water. Doesn't seem to be working though, does it? I don't see any bubbles, do you? No. Water does absorb carbon dioxide gas, but I don't have a fizzy drink. Weird. Time to check the book of science. Oh, in order to make bubbles, you have to have pressure. So... This is an air compressor. It takes air and compresses it, puts it under pressure. So... The container needs to be pressurized. Okay. When you get a container of a fizzy drink, the carbon dioxide gas is put in there under pressure, and it stays in there under pressure until you release it. That's the sound of the pressure being released. And when it is released, the carbon dioxide gas starts to expand. And when it expands, it creates bubbles. And that's what makes your fizzy drink. This process takes a while to run out, but eventually it will become flat. No more bubbles. But what if there was a way to release all of that carbonation all in one go? Well, there is. And for this experiment, all you need is your favorite brand of fizzy drink, Science Max brand Diet Science Cola, 100% science, 0 calories. And your favorite candy, like these Science Experiments. All the minty flavor that comes from pure science. So, all you need to do is open this up, take one of these, and put it in here with an adult's permission because it can get kind of messy. Whoa! What's going on here is all of the carbonation that was in the bottle is now being released much more rapidly than it would have been before. Now, why does this happen? Well, if you look at a carbonated beverage, you'll see that the bubbles don't come from everywhere. They come from the inside of the glass, or in this case, a lot are coming from the straw. And that's because the carbon dioxide bubbles like to find a little imperfection, something to hold on to in order to expand and bubble out. And a candy, such as this, has a ton of little tiny microscopic imperfections. So when you drop it in, there's a lot more places for the bubbles to attach, and that makes the carbonation happen a lot quicker. But remember, this is not a chemical reaction. It all has to do with carbonation. So that's what we're gonna be looking at today. Air pressure, more pressure, less pressure, and of course, we're gonna be maxing out this experiment. All right, I just need an expert to help me max this out. Let's see, oh, Cynthia from the Ontario Science Center. She'd be perfect for this. All right, and good. Okay, come on, let's go. And, yep, that's good. Oh, hey, Cynthia.
Hey, Phil, how's it
Cynthia
going?
from the Ontario Science Center. You're gonna help me max out the science experiments and diet science cola experiment. I think we need a better name for this.
Okay, well, we have the mints that have tiny little pores called nucleation sites on them. The gas inside the cola is gonna go through these nucleation sites, create a giant fountain. So why don't we call it a nucleation fountain?
Ooh, nucleation fountain. I like that. It's accurate and it sounds awesome.
There we go.
Okay, so we want to max it out. So how many should we put in?
Let's say 5 more nucleation sites.
More reaction. Ah. I tried adding more mints, but one at a time didn't work. It doesn't,
No.
it's not, the bubbles are pushing it back out again. There we go, there we go. And then, yeah, I think if we put them all in at the same time, it would work better.
So we came up with a delivery mechanism to get all the mints in at the same time. A tube with a magnet holding the mints up, which we screw onto the top of the bottle. Pull the outside magnet to release, and
Oh, nice.
Yeah,
Oh, yeah.
that's a good fountain.
That is
a
a
good nucleation fountain.
Nucleation fountain worked very well.
There we go.
Cynthia and I decided to try some other ideas to max it out even more. We decided to do some
Experimentation.
Experimentation.
Oh, that's a good one. Yep.
and see if Diet Cola was the best carbonated drink to use. We tried 4 different kinds: Diet Cola, regular cola, lemon lime soda, and club soda.
Really just
It's just carbonated water.
carbonated water.
3, 2, 1, go. Whoa. Science cola. But I think that it was close.
I think it was the release.
Let's watch the replay.
Okay.
Yep, Diet Science Cola went the highest.
So the next step is,
Maybe if we want to max the size of the fountain, we have to make a narrower stream.
ooh, so a smaller aperture opening will be higher pressure
That's what I'm thinking.
because it'll be forced at a smaller opening. What else can we do?
We can launch it.
We could launch, oh, you mean like sideways?
Yeah.
Yeah, I love that idea. So we'll put it on wheels. We'll put it on wheels.
Okay.
And then we'll launch it sideways.
Okay.
We got a lot of things to do. Okay, let's get.
We need time. Let's do it.
Get to it. Okay, we'll go to
Okay.
the lab. I'll get a mop. Nothing like a fizzy glass of water. And now there are ways for you to carbonate water at home with something like this, the Science Max Carbonation Station. You have a bottle of compressed carbon dioxide gas that's hooked up.
You take a bottle of tap water, attach it, and carbonate it.
Voila! Carbonated water. But this is Science Max. Why just carbonate water? Let's carbonate everything! Let's carbonate pickle juice. It's actually amazing. Milk! It's like milk meets water, kind of very odd. Chocolate milk? Oh no, that's way better. Carbonated mustard. Carbonated tomato juice? Carbonated hot sauce. No, wait, carbonated. That was the hot sauce. No. Carbonated clam chowder. Oh, there you go. Carbonation, not just for water anymore. It is definitely not for clam chowder. No, that's just a big bowl of no. Never again.
Cynthia and I are maxing out a nucleation fountain.
Yeah.
Oh,
That's a good fountain.
We're changing our design a bit to see if a smaller hole in the bottle cap will make for a higher pressure fountain, which will make it more maxed out.
We have this large hole. We've got a medium-sized hole.
We have a very small hole
So we're gonna see large, medium, or small, which one is the best.
to max out our fountain.
Exactly. But the problem is that our old delivery mechanism won't work if we keep the cap on. So we needed to come up with a new delivery system. So we drilled holes in the mints and put them underneath the cap on a pipe cleaner. They hang at the top of the bottle until we pull the pipe cleaner, and then they fall in.
All right, are you ready?
Oh, I'm so excited. Which one do you predict will be the best? This will have a larger geyser.
I
These
think
ones
this will
be smaller.
look cooler
Yeah.
because it'll be big, but this one,
The smallest hole, I think, will go the highest.
yeah. Ready?
Three,
2,
two,
1. Definitely the biggest.
There. Whoa, careful, careful, careful. Whoa.
This one is almost like a spray.
It's not like a mist.
Yeah,
it's a
a
mist of
mist.
cola. They all kind of worked a little differently. The interesting thing is this one lasts the longest.
Oh.
There we go. So, this was cool, but not the best.
This one's still going.
It's still
It's
going.
not over yet.
You gotta give it points for still going.
I think this fountain looked the best, though.
This one was pretty good. So, a small aperture, but maybe not the smallest aperture would be the best. So because of the force coming out of here, I think that we could probably do something like putting it on wheels.
And shooting it like a rocket?
Yeah, let's see.
On wheels?
Or like a car.
Oh.
Yeah, we'll make a nucleation fountain car. The Nucleation 1!
It's our race car.
It's our race car. It's got fancy wheels that spin really well.
And we decided to go with the medium aperture. So it's fairly big, but not too small.
Yeah, all we need to do is unscrew that, put that in there, and then pull it out.
3, 2, 1. Oh, good. Let it go. Oh, that's not so bad.
Whoa, yeah!
Missed the finish line.
Past the thing! Turn it around, turn it around! Whoa.
Do you think we can make it get to the finish line?
It's
no.
spinning out.
Oh, wow.
Go! There. Yeah!
It worked pretty well, but there's always more ways to max it out.
What if we just got like a giant container? Like, because we're using small containers, right? What if we just
So
got a
you
really
want to
large
carbonate
container?
a very large container.
Well, we'd have to figure out some way to, well, come on, let's go figure it out.
Okay, let's do it.
This is an egg. It's been hard-boiled and peeled, so there's no shell on it. This is a flask, and this is hot water. I pour the hot water into the flask, which means the air inside the flask starts to heat up. And when it heats up, it expands, and some escapes through the top of the bottle. I pour the water out, and then I cap the flask with the egg. Now this expanded air is starting to cool again, which means it's lower pressure, which means the higher pressure on the outside of the flask pushes the egg in. Ha-ha! Fun! And then, to get the egg out, I can reverse it. If I blow into the flask, I can increase the pressure inside. Science! And now let's max it out. Max out container! Okay, pour out the water. Oh, careful, careful. And now, I put this water balloon on the top, and we'll just see what happens. The hot, expanded air inside the container is cooling and reducing in pressure, which means the higher pressure outside the container,
It's happening.
pushes the balloon in.
It's happening. Oh. Success! Maxed out.
Did you know that we live on the bottom of an ocean of air? It's called the atmosphere. And compared to the Earth, it's really thin. I mean, it's about as thin as this. Huh? Look at that, not very thick at all. But it's a good thing the atmosphere is around, and not just for breathing. Though I am a fan of breathing. What do we want? Breathing! When do we want it? All the time. But did you know the atmosphere has different layers? It's true. I will walk you through them. No, I mean, come on, you gotta come with me. I'm walking over to walk you through them. Okay, the troposphere. This is the layer where we are all existing right now, where all of our weather happens. There's a lot of air molecules in this layer. Think of these balloons as air molecules. There's a lot of air in this layer. Yay, air! Yeah! Next layer, the stratosphere. There's less air molecules in this layer, and it's where jets fly. Next layer, the mesosphere. There's even fewer air molecules in here, and it's where meteors burn up and turn into shooting stars.
Fire, 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 fire!
The thermosphere. Not many air molecules left up here, and this is where the northern lights, the auroras, happen. Woo! Northern lights. And finally, the exosphere. This is as high as the atmosphere goes. This is where satellites orbit, and if you see any air molecules up here, they're just passing through.
Hello.
And after that, nothing but the vacuum of space.
Ooh, the vacuum of space.
Of course, you know it's not that kind of vacuum, right?
Right, vacuum just means no air. There you go, the atmosphere. The only thing separating us from the vacuum of space. Roberta, the space vacuum got broken. I don't know how.
Cynthia and I are maxing out the Nucleation fountain.
This one is almost like a spray.
It's not like a mist.
Yeah,
It's a mist of cola.
Just to experiment, we tried using a giant bottle and pouring the Diet Cola in.
I'm a little concerned about the science.
But it didn't work.
Well, that's not very exciting.
Okay, so that didn't work at all.
No,
This is not a chemical reaction.
it's a physical change.
So it's the carbonation that matters.
Exactly.
When we poured the cola into the bottle, we lost almost all the carbonation.
How are we gonna max it out?
That's the question. So if we can't make a larger container,
More bottles?
we just have more bottles. So we'll just get a
Exactly.
lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something. We'll max out the
I know.
fountain.
You know, we should be sort of like a cascade and we'll get a lazy Susan or This is a vacuum chamber. It's an airtight container, and I put a hose on it, and the hose is attached to a pump. Now, the pump takes the air out of the chamber, creating a vacuum. So, let's have some fun putting things in a vacuum chamber. Marshmallows in a vacuum chamber. The marshmallows grow larger,
Whoa!
then shrink much smaller when returned to normal pressure. Why? Well, take a look at what happens with this balloon. The vacuum takes the air and the pressure out of the container, which was pushing against the sides of the balloon. Without that outside pressure, the air molecules inside the balloon can expand. So let's max it out with
Maxed out marshmallow.
just like the balloon, the marshmallows expand. But unlike the balloon, the air in the marshmallows escapes, so they shrink when the pressure is added back in.
They're almost the size of regular marshmallows.
It's the air inside a marshmallow that makes it fluffy.
It's not very fluffy.
The same expanding process happens with marshmallow cookies.
The marshmallow has completely deflated and it's all kind of hollow inside.
The frosting on a cake.
More cake! No, no! Oh! Look at this giant birthday cake. I can't wait to eat it. No! No! Why? Birthday cake!
And even shaving cream.
No! Shaving slime.
Cynthia and I have done a whole bunch of different experiments
Experiments.
to find out how to max out the Nucleation fountain.
So we'll just get a lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something.
Now we have a bunch of bottles and we're ready to try the maxed out version.
We've got our release mechanism.
With our medium aperture.
Yep, and we're gonna put the mints in all of the bottles and then we're gonna release them in a very coordinated,
Pattern.
rehearsed pattern.
very rehearsed.
We've rehearsed it a couple times. We'll see how it goes. And we've got this lazy Susan, which will spin around, and we'll see how it goes. And 3,
2, 1. 1,
2,
3,
4,
5,
6,
7. Surprise! 1, 2, oh, go, 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 3, 4. We did it!
Whoa!
It's raining Diet Science Cola. We maxed it out!
Maxed out! Nucleation fountain. That is as good as it's gonna get. So let's recap. Our nucleation fountain is all about releasing the carbonation in our Diet Cola faster than normal. This happens because there's lots of tiny bumps on the mints for the carbon dioxide to grab onto and make bubbles. High fives. There you go. Science Max, experiments at large, nucleation fountain. Excellent job. Now all we need to do is clean it up.
Clean up, and I think I need a shower with water.
Yeah, I think I need at least the towel.
Yeah,
Okay,
but it's supposed to volumize your hair.
Is it good for
I
your
think
hair?
So.
I
Yeah,
hope so.
better than honey and things like that.